3. Look around you. The room you are sitting in, the device you are listening to, the solid ground beneath your feet. It all feels deeply predictable. If you leave a cup of coffee on your table and walk out the door, you know with absolute certainty that it is still there, existing in exactly the same state whether you are looking at it or not. Albert Einstein believed this too. It is a concept we call local realism, and it forms the absolute bedrock of our everyday human experience. Einstein argued fiercely that the universe has definite properties independent of our observation, and he insisted that nothing, absolutely nothing, can ever travel faster than the speed of light. But what if I told you that the most brilliant physicist of the 20th century was completely wrong about the fundamental nature of reality? Recent breakthroughs in the quantum world have achieved the unthinkable. They have entirely shattered Einstein's oldest and most stubborn conviction. We have discovered that the universe does not behave like a predictable clockwork machine. Instead, we have found particles that are inextricably linked, communicating instantly across vast oceans of empty space, seemingly mocking the cosmic speed limit. Einstein hated this idea so much that he famously dismissed it as spooky action at a distance. Yet, the final experiments are in, and that spooky action is entirely real. If you are ready to leave behind the comforting illusions of your everyday world and uncover the true nature of the cosmos, take A to subscribe to Greene Theory. Together, we are going to unravel the deepest mysteries of existence. Today, we are going to explore the exact moment the classical world broke apart. We will discover how quantum physics proved Einstein wrong and what it actually means for the fabric of reality itself. I want you to think about a game of billiards. Imagine walking into a dimly lit room, the green felt of the table illuminated by a single overhead lamp. You take your cue, line up your shot, and strike the white cue ball. Hurry, you know exactly what is going to happen next. The cue ball travels across the table, hits the red ball, and sends it hurtling toward the corner pocket. Even if you close your eyes the very fraction of a second before the impact, you know the red ball is still there. You know it is still rolling. You know it will eventually drop into the pocket with a satisfying thud. This is the essence of how we have understood the universe for centuries. We call it classical mechanics. It is the physics of Sir Isaac Newton, and it is the physics of your everyday life. It is built on a profoundly intuitive assumption about reality, an assumption so deeply embedded in our minds that we never even pause to question it. In physics, we call this dual assumption local realism. Let us break that down, because it is the key to everything Einstein fought to protect. Realism is the belief that objects in our universe possess definite pre-existing properties, regardless of whether anyone is measuring them. The moon is still shining in the night sky, even if every single person on Earth looks away. The red billiard ball has a specific mass, a specific speed, and a specific location at all times. It does not exist in a blur of possibilities. It is real and it is definite. The second half is locality. Locality is the strict rule that an object can only be influenced by its immediate surroundings. If I want to move a coffee cup on my desk, I cannot simply wish it to move. I have to physically reach out and touch it, or I have to throw something at it, or perhaps a gust of wind has to blow against it. There must be a chain of cause and effect traveling through the space between us. And crucially, Albert Einstein proved that this chain of cause and effect has a hard, unbreakable speed limit. Nothing, not a physical object, not a signal, not a ripple of information can travel from one place to another faster than the speed of light in a vacuum. That is roughly 300,000 kilometers per second econd. It is the absolute speed limit of the cosmos. For Einstein, local realism was not just a theory. It was a philosophical necessity. When he rewrote the laws of space and time with his theory of relativity, he maintained this absolute foundation. He showed us that time can bend and space can warp. But he firmly believed the universe was still a fundamentally reasonable place. The universe, in his view, does not play dice, and it certainly does not allow for magical, instantaneous connections between distant objects. But as we moved into the 1920s, a new generation of physicists began looking closer at the fabric of reality. They stopped looking at stars and billiard balls and started looking at the microscopic building blocks of existence. Atoms, electrons, and the tiny packets of light we call photons. Down in this microscopic basement of the world, they found a reality so bizarre, so completely alien to human intuition, that it threatened to tear down the beautiful, predictable cosmos. Einstein had described. They called this new frontier quantum mechanics. And the pioneers of this field began to realize something deeply unsettling. When you look at an electron, it does not behave like a tiny billiard ball. Before you measure it, an electron does not seem to have a definite location or a definite spin. It exists in a haze of probabilities, a cloud of potential outcomes. The mathematics suggested that only when you force a measurement, only when you observe it, does it snap into a definite reality. Einstein rejected this fiercely. He argued that if quantum mechanics said reality is undecided until we measure it, then the theory was simply incomplete. He believed there must be hidden gears and levers beneath the surface, very secret instructions inside the particles that we just could not see yet. He spent the rest of his life trying to find those hidden gears. He was desperate to save the clockwork universe. But as we will soon see, the universe had other plans, and the ultimate test of Einstein's belief would come down to an idea so strange. It feels like science fiction. To understand why Einstein was so deeply troubled, we have to talk about a phenomenon called quantum entanglement. It is without a doubt the strangest and most unsettling feature of the quantum world. I want you to imagine I have a simple pair of winter gloves. One is a left glove and one is a right glove. I put each one into a separate, completely identical box. I shuffle the boxes around so you have absolutely no idea which is which. I hand one box to you and I take the other box with me on a rocket ship and fly all the way to the planet Mars. Up to this point, this is purely classical physics. It makes perfect sense. The gloves have definite pre-existing properties. My box contains either the left glove or the right glove. It is a set reality. Even if I have not looked inside yet, when I land on Mars and open my box, if I see the left glove, I instantly know that you are holding the right glove back on Earth. Now, did any magic happen here? Did my looking at the left glove instantly send a signal to Earth to turn your glove into the right glove? Of course not. The gloves were already left and right the entire time. No information traveled faster than light. But in the 19 and 30 seconds, the mathematics of quantum mechanics predicted something entirely different for atomic particles. It predicted that two particles, perhaps two photons of light, could be created together in such a way that they become deeply intimately linked. They share a single unified quantum state. We call them entangled. If our winter gloves behaved like entangled quantum particles, the mathematics said something that completely defies common sense. It said that while the gloves are in their closed boxes, they do not possess a definite left or right-handedness. They are not one or the other. They are actually a mixture of both possibilities at the exact same time, existing in a blurry haze of probability. The physical reality of the glove is literally undecided. It is only at the precise fraction of a second that I open my box on Mars and measure my glove that it is forced to choose. It snaps into existence, let us say, as the left glove. But here is the part that caused a profound crisis in physics. Because the two items are entangled at the exact moment, my particle on Mars assumes a definite state. Your particle back on Earth instantly, with absolutely zero time delay, snaps into the opposite state. In 1935, Albert Einstein, along with two brilliant colleagues, Boris Podolsky and Nathan Rosen, published a paper that struck at the very heart of this idea. They used this exact scenario to point out what they saw as a fatal, undeniable flaw in quantum theory. Einstein argued that if quantum mechanics were true, measuring a particle in one location would instantly dictate the reality of a particle millions of miles away. He famously mocked this idea, calling it spooky action at a distance. He despised the concept. Why? Because it directly violated the most sacred rule of his own theory of relativity. Remember, the speed of light is not just a cosmic speed limit for space travel. It is the fundamental speed limit for cause and effect. If my measurement on Mars instantly decides the physical reality of your particle on Earth, It means some kind of invisible influence has traveled through the vacuum of space faster than light. And if you can send a signal faster than light, the mathematics of relativity show that you break the fundamental flow of time itself, you could theoretically have an effect happen before its cause. Therefore, Einstein concluded the quantum physicist must be wrong. The theory had to be incomplete. He believed that entangled particles must be exactly like our ordinary classical gloves. They must contain hidden variables. He thought there must be secret internal instructions encoded within the particles from the very beginning, telling them what properties to reveal when measured. We just lacked the technology to see those hidden instructions. Einstein went to his grave believing the universe was sensible, that reality was local, and that nothing was truly spooky. For 30 years, this remained a quiet philosophical debate. It was a beautiful argument of ideas, but it seemed completely untestable in any laboratory. The scientific world moved on, but the mystery was only sleeping, and a brilliant Irish physicist was about to wake it up in a way that would change everything. For nearly 30 years, the physics community essentially ignored Albert Einstein's warning. The equations of quantum mechanics worked perfectly. They allowed us to build lasers, transistors, and the early foundations of the computer age. Most physicists simply did not care about the philosophical paradox occurring behind the curtain, but the mystery was still there waiting. In 1964, an Irish physicist named John Stuart Bell was working at the CERN laboratory in Switzerland. Bell was deeply troubled by the exact same things that bothered Einstein. He wanted to know the truth about reality. Was the universe a predictable machine with hidden instructions, or was it a spooky web of instantaneous connections? Bell realized something absolutely brilliant. He found a way to drag this purely philosophical debate out of the clouds and force it into the harsh, unforgiving light of a laboratory experiment. To understand the genius of what Bell did, I want you to imagine a classic detective story. Picture two criminals who have just pulled off a major bank heist. The police catch them, but before the suspects can talk to each other, the detectives lock them in completely separate, soundproof interrogation rooms. The detectives want to know if these two suspects are just guessing what the other is saying, or if they have a perfectly planned alibi. So, they start asking questions. If the detectives ask both suspects the exact same question, like what color was the getaway car, and they both say blue, it does not prove anything magical. It just means they agreed on the color blue before they got caught. This is Einstein's hidden variables. They had a pre-existing plan, but John Bell figured out a way to break this plan. He realized that if the detectives started asking completely random mismatched questions, asking suspect A about the car and asking suspect B about the bank vault, they can test the limits of the alibi. If the suspects are relying on a pre-planned script, there is a strict mathematical limit to how often their answers will perfectly correlate. They simply cannot anticipate every single random combination of questions the detectives might ask. Bell translated this detective story into the mathematics of quantum physics. Instead of suspects, we have two entangled particles, like photons of light, flying away from each other in opposite directions. Instead of detectives asking questions, we have scientists using polarizing filters to measure the spin or the angle of those particles. Bell proved mathematically that if Einstein was right, if the universe respects local realism and particles carry secret pre-planned instructions, then the correlation between the measurements must always fall below a certain strict limit. This mathematical boundary became known as Bell's inequality. It is the absolute limit of what a classical predictable universe can achieve. But Bell's equations also showed the other side of the paradox. If quantum mechanics was the true rule of the universe, and the particles were genuinely communicating instantly, they would be able to cheat the interrogation. They would be able to coordinate their answers on the fly, and their measurements would break through Bell's inequality limit. This was a breathtaking moment in the history of science. John Bell had just drawn a line in the sand. He proved that you could not just politely agree to disagree. The mathematics were totally incompatible. The universe had to be one or the other. Either it is local and real, just as Einstein demanded, or it is non-local and deeply fundamentally weird. For the first time in human history, the true nature of reality could be tested. We did not have to argue philosophy anymore. All we had to do was build the experiment, create the entangled particles, ask them random questions, and see if they broke Bell's absolute limit. There was only one problem. In 1964, the technology required to conduct this experiment was incredibly primitive. Firing single particles of light, controlling them and measuring them with the required precision was thought to be nearly impossible. The paradox had been perfectly defined on a chalkboard, but the truth remained locked away, waiting for someone daring enough to build the ultimate interrogation room. It took years for anyone to actually build the experiment John Bell had dreamed up. The technology was simply not there in the 1960 seconds. But physicists are notoriously stubborn, and the question at stake was too profound to ignore. In the early 1970 seconds, a young American physicist named John Clauser decided he was going to try working with scavenged parts in a basement laboratory. He built a machine that fired calcium atoms, causing them to emit pairs of entangled photons in opposite directions. He set up detectors to catch them and measure their properties. And when the data came back, it gave the first terrifying hint that Albert Einstein was wrong. The particles were breaking Bell's limit. But there was a problem. In physics, we are terrified of loopholes. Skeptics argued that Clauser's detectors were fixed in place. They were essentially asking the photons the same questions for a long period of time. What if the machine was somehow leaking information? What if a signal traveling at the speed of light or slower was passing between the two sides of the experiment, whispering the answers back and forth? If that were happening, Einstein's local, very predictable universe could still survive. To finally crush this loophole, to force the universe to reveal its ultimate secret, we needed to do something that will absolutely break your brain. In 1982, a French physicist named Alain Aspect realized that to prove spooky action at a distance was real, he had to change the rules of the interrogation. He had to change the question the detectors were asking while the photons were already flying through the air. I want you to think back to our detectives and the bank robbers. Imagine the detectives are walking down the hallway toward the interrogation rooms, but they do not know what questions they are going to ask yet. They decide to flip a coin while their hands are turning the doorknobs, deciding at the very last microsecond whether to ask about the getaway car or the bank vault. There is physically no time for the suspects to hear the question, invent an answer, and secretly radio their partner. Even if the suspects had invisible transmitters broadcasting at the absolute speed limit of the universe, the speed of light, the signal simply would not arrive in time. The gap is too wide. The clock is ticking too fast. Alain Aspect did exactly this, but with particles of light. He built a breathtakingly complex system of switches that could redirect the photons into different polarizing filters in 10 billionth of a second. The photons were traveling at 300,000 kilometers per second each. But the detectors were changing their settings drastically faster than light could ever travel the distance between them. There was no physical way in the entire framework of classical physics for one photon to know what question was being asked of the other. The speed of light strictly forbade it. The switch was flipped. The photons flew. The random questions were asked. And what happened? The data poured in clear and undeniable. The photons shattered Bell's limit entirely. They cheated the interrogation. Even though they were separated by space, and even though there was zero time for any physical signal to cross that gap, they perfectly coordinated their reality. When one photon was forced to choose a specific state, the other photon instantaneously snapped into perfect alignment. Not a fraction of a second later, not after a delay. Instantly. This is the exact moment the clockwork universe died. Listen to me closely, because this is where human intuition simply fails. The experiment proved that Einstein's hidden instructions do not exist. The particles do not have a pre-planned script. The universe is actually deciding what is real at the exact moment the measurement occurs, and it is doing so across the vastness of space without any physical connection whatsoever. Years later, a physicist named Anton Zeilinger took this even further. Beaming entangled photons between mountain peaks in the Canary Islands separated by hundreds of kilometers, the result was exactly the same: instantaneous connection. This means the physical distance between two entangled particles means absolutely nothing. Whether they are separated by 2 meters in a laboratory or two ends of the Milky Way galaxy, they act as a single unified system. They share one reality completely unbound by the constraints of space and time. Local realism is a perfectly crafted illusion, and the true foundation of our universe is profoundly, deeply spooky. So what do we do with this information? The experiments are completely bulletproof. The data is absolute. Alan Aspect, John Clauser, and Anton Zeilinger were awarded the highest honor in science for proving that this instantaneous connection is a fundamental fact of nature. They forced us to confront a beautiful and terrifying realization. The hard truth is that the universe you think you live in, the one governed by common sense and predictable rules, does not actually exist. Local realism is dead, and because it is dead, we are forced to make a brutal choice. We have to sacrifice at least one of the deeply held beliefs that construct our everyday human experience. We must either give up realism or we must give up locality. If we give up realism, we must accept that the physical universe literally does not exist in a concrete state until it is observed or measured. The fundamental building blocks of nature are just ghostly probabilities waiting for an interaction to force them into a solid reality. If we give up locality, we must accept an even stranger truth. We must accept that distance is essentially an illusion. We must accept that two objects on opposite sides of the visible universe are in some profound fundamental way right next to each other. They are touching in a framework of reality that our physical brains are entirely unequipped to perceive. Space is not simply an empty container that separates things. It is a deeply woven web of instant, very invisible connections. Most physicists today will tell you that we have likely lost both. Now, I know exactly what you are thinking. You are looking at the solid objects around you and asking, if the universe is this deeply weird, why is my everyday life so perfectly normal? Why does my car not exist in a hazy blur of probability? Why do I not feel instantly connected to the surface of the moon? The answer is that the macroscopic world you live in is messy and crowded. It is made of trillions upon trillions of atoms. In the quantum realm, entanglement is incredibly fragile. The precise moment a delicate entangled quantum particle bumps into a random air molecule or a stray particle of light, the spooky connection breaks. The wave of probability collapses. We call this process decoherence. Your everyday environment is constantly interacting with itself. It is constantly being measured by the billions of particles bouncing around every single microsecond. The macroscopic world is essentially forcing itself to act normal. But do not let that fool you into thinking the quantum world is just a microscopic quirk. The spooky action at a distance is the foundation of absolutely everything. And we are no longer just philosophizing about it. We are actively engineering it. Right now, humanity is taking this exact bizarre phenomenon and using it to build the future. We are building massive quantum computers. Instead of classical computer bits that are forced to be a simple 0 or a 1, we are carefully isolating individual particles, entangling them and allowing them to exist in that hazy blur of multiple states at once. We are designing machines that calculate inside the phantom realm of endless possibilities. By harnessing the exact spooky action that Einstein hated, we can solve complex problems in seconds that would take a normal classical machine millions of years to crack. This is not theoretical science fiction. It is happening right now in laboratories across the globe. It proves that this spooky action is not a mathematical glitch. It is the true operating system of the cosmos. And this leads us to the most staggering thought of all. Physicists are now exploring the mathematical possibility that quantum entanglement is not just something that happens inside of space. We are beginning to suspect that entanglement is the very thing that creates space. Without these invisible instantaneous threads tying particles together, the three-dimensional fabric of space-time itself might completely unravel into nothingness. Albert Einstein spent the last decades of his brilliant life trying to prove that this spooky action was impossible. He believed it would break reality. But the hard truth is far more poetic. Spooky action at a distance is not the thing that breaks reality. It is the invisible glue that holds reality together. I want you to bring your attention back to the room you are currently sitting in. Look at your own hands. Feel the solid weight of your body. It is incredibly easy to feel like you are a separate, isolated individual moving independently through an empty, disconnected universe. But the ultimate climax of this quantum mystery is that your feeling of separation is nothing more than a localized illusion. Let us take the logic of quantum entanglement to its absolute limit. Every single atom that constructs your skin, your bones, and the blood pumping through your veins was not created here on Earth. Those atoms were forged billions of years ago in the crushing nuclear furnaces of ancient stars. When those massive stars finally died, they exploded in violent supernovas, scattering their newly forged elements across the empty void of space. Those scattered fragments eventually drifted together to form our solar system, our planet, and eventually you. But we must go back even further. Before the stars, before the galaxies, roughly 14 billion years ago, absolutely everything in the observable universe was compressed into a space infinitely smaller than a single grain of sand. All the matter, all the energy, all the potential for every planet, every star and every human being that would ever exist was crammed into a single unimaginably dense microscopic point. At that exact moment, the entire universe was in absolute intimate quantum contact. Every particle was perfectly interacting with every other particle. The entire cosmos was in a state of supreme universal entanglement. Then came the rapid expansion we call the Big Bang. Space violently tore itself outward, stretching and expanding to create the massive dark void we look up at every night. But if the laws of quantum mechanics hold true, and we have every reason to believe they do, that primordial entanglement was not simply erased by distance. The universe expanded, but the fundamental invisible quantum threads connecting all things were stretched along with it. We are not simply observers standing on the outside looking in at a mechanical clockwork universe. We are deeply interwoven into the very fabric of reality itself. We traded the cold, lonely universe of Isaac Newton and Albert Einstein for a deeply responsive, entangled cosmos. The space between us is not empty. It is a vibrating, unseen web of instantaneous connections. Exploring these mind-bending concepts takes a tremendous amount of time, deep research, and a relentless dedication to the truth. Uncovering the mechanics of reality is a journey we are taking together step by step. If this shift in perspective has brought you value today, if it has shattered your classical view of the world and given you a genuine glimpse behind the cosmic curtain, I want to invite you to support this mission. Right beneath this video, you will find the Super Thanks button. Every single contribution goes directly into funding the research and production of this channel. Your support is the vital energy that allows me to keep asking the biggest questions in existence, to keep peeling back the layers of reality, and to keep bringing these deep cosmic truths directly to you. I am profoundly grateful for your partnership in this journey of discovery. Let us return one last time to the brilliant man who started this entire debate. Albert Einstein lost his fight to save local realism. The spooky action at a distance that he mocked and despised turned out to be the undeniable truth of nature. But we must never view Einstein as a failure in this story. In fact, his stubbornness is exactly what saved us. If Einstein had not fought so fiercely, if he had not written that brilliant paper in 1935 demanding that reality make sense, John Bell would have never been inspired to write the mathematics that tested it, and Alain Aspect would have never built the impossible machine that finally proved it. Einstein's desperate attempt to destroy quantum mechanics accidentally gave us the exact map we needed to prove it was real. By trying to save the clockwork universe, he ended up giving us the keys to the quantum tapestry.